Okay, this is a different type of problem than we have done. It gets back to kind of putting the thermodynamics and the gas together. So work is done by the system when the volume changes against an external pressure. And this is what makes gases useful to humans to be able to do work. So a 100-watt electric heater, so a watt is how quickly it uses energy, so 1 joule per second, operates for 20 minutes to heat the gas in the cylinder. The gas expands from 2 to 2.5 liters against an atmospheric pressure of 1 atmosphere. What is the change in energy of the gas? And 1 liter atmosphere is 101.325 joules. So you'll see that connection there to the work unit or the pressure unit or the work unit of joules. It's the pressure. It's pressure working through or against a volume change. So you have a couple things to do. You have this time factor, so you can kind of see the joules per second. So I'm going to start with how long this runs that's going to determine. So it's going to be a bridge problem with 20 minutes. And I'm going to convert that to joules. So that's just going to be a quick 60 seconds in a minute. And 100 joules per second. So that's going to give me 1.2 times 10 to the 5th joules. And then I have that delta E equation from the first page of thermodynamics equals Q plus W. So this is my Q factor. And that's my heat. And then work is equal to pressure times change in volume. So I'm going to work on that. So I have 1 ATM. And that's going to go to 2.5 liters minus the 2 liters. You could just put 0.5 liters in there. That's where it comes from. And then I'm going to do the 101.325. Joules is equal to a liter atmosphere. Okay. And it's going out, so that's going to be an exothermic change. So this is going to be negative. And that's going to give me negative 51 joules. Then I just need to put my two factors together. So 1.2 times 10 to the 5th joules. And this is Q minus PV. Since this was a negative, it's going to be negative 51 joules. So again, because this factor is so large, it really doesn't make a difference. The work done is really small because it's such a small change in volume. So we need a bigger change in volume for this work to be significant. It's just not significant in this problem. It is significant in real life. You have lots of changes, and those happen multiple times inside in a cylinder, so that's why cars move. The next type of problem applies gas laws to heat and reactivity. So we're going to have an equation this time. So the oxidation of nitrogen in the hot exhaust of jet engines and automobiles occurs by the reaction. N2 plus O2 yields 2NO with the delta H value of positive 108.5 kilojoules. That's an endothermic reaction. So how much heat is absorbed in the oxidation of 17.4 liters of nitrogen at 1 ATM and 273. So again, I've got volume, I have pressure, and I have temperature. So this is going to be a PV equals nRT if it's solved for N. So N equals PV over RT. And just always check your math when you're solving for one of these. Make sure when you cross multiply, you get PV equals RT, so you don't get variables upside down. So I'm just substituting in. So I'm substituting in 1.0 atm pressure, 17.4 liters per volume, 0.0821 liter atmospheres per mole Kelvin, so making sure my units cancel there. And then multiplied by 273 Kelvin. So it was nice that they already gave that one to us in Kelvin, so it's just a matter of calculating that one out. And that's going to give me 0.776 moles of N2. And we want to know heat, so we're not done just finding moles. We've got to convert that to the 180.5 kilojoules per mole. And that's going to give us 140 kilojoules. Next part of the question, when the oxidation of nitrogen to nitrogen monoxide was completed in a bomb calorimeter, the heat absorbed was measured at 790 joules. What mass of nitrogen oxide was oxidized? So I'm going to start this part B with 790 joules. And again, I could have gone directly to kilojoules, but we'll show 1,000 joules to a kilojoule. So heat is given. So I have 1 mole of N2 for my 180.5. Again, this is the value given in the reaction. And I'm using the molar mass of N2 of 28.02 grams and 1 mole. And that's going to give me 0.123 grams. And AP is notorious for throwing gas law problems in with other topics, so I think this is something that you're going to see on the exam. Okay, next problem. This is a little longer. 200 milliliter sample of hydrogen chloride at 690 to 220 degrees Celsius is dissolved in 100 milliliters of water. So again, this is telling you it's a gas. Then the solution was titrated, so that tells you there's a chemical reaction going on for the stoichiometric endpoint. So, i.e., all your acid was neutralized with 15.7 milliliters of a sodium hydroxide solution. And it wants to know what's the molar concentration of the NaOH solution. So again, it doesn't really matter what order you do this, but as soon as I see stoichiometry, I'm thinking balanced equation. And this one's a pretty basic one, so NaHCl. And I'm going to get water and sodium chloride. And this one is a nice one because it's just a 1-to-1. So I don't have to do anything to balance that. So all of this information here, I have a volume, I have a pressure, and I have a temperature, and I have a volume of water. So this is basically just information that you're going to need. So the water's not in gas form, so this will be kind of a molarity idea that's liter. So we're going to start with figuring out how many moles of gas. So this is going to be N equals PV over RT again. So solving for N gives me PV over to RT. I'm going to substitute in to figure out how many moles of HCl I have. When I substitute in, I'm going to have 690 torr times the 200 milliliters has to be converted to liters, so I didn't show the bridge problem. If you need to show that, that's fine, but you can mentally do that. That's going to convert to 0.200 liters. Since they gave it torr, I'm going to use the 62.36 R value to get my torrs to cancel. And liters cancel, so if you use milliliters and you follow along with your units, you should be able to catch that mistake. And then at 273K. If you substitute in directly as 293, that's okay also. And that whole calculation is going to give you 0.00755 moles of HCl. So that becomes my starting point in my bridge problem for the stoichiometric part. I have the 0.0075 as my starting quantity, and I'm looking for molarity, so I'm looking for moles per liter as my final. So this is HCl here, so I need to show them all. So if you skip this step, you may not get full credit on the exam. So 1 mole of HCl is 1 mole of NaOH, and I know it's 1 to 1, but you need to show that you understand that we are converting from one substance to another. Now, that's going to give me the mole part. The liter part is a little trickier. So here's where this 100 milliliters comes in. So it's the water plus what we titrated in. So it's going to be 115.7 milliliters is my volume. And you could have put that over here as well, it doesn't matter. And then I need that converted to liters. And again, if you can do that directly, that's okay. But that is going to give you a total molarity of 0.481. So again, you see how as we move through the year, we're going to be applying other concepts and kind of continually review as we go.